Okay, back to this slide. Okay, as I mentioned previously, okay, we know that our angular moment is equal to I d omega over dt. So the I play as an important role in order for you to remain the what we call it moment of to remain the angular moment, the net torque. For example, m is I over ia, or I the differentiation of d omega over dt. In order for you to remain in order for you to remain the same of net torque, so you need to play around with the I and also alpha, or I also and omega, your omega. So if you have high moment of inertia, what happen is your omega will be lower. If you want a high omega, you need to reduce your I. Okay, if you have high omega, so same like this. So in order to make it faster of your rotation or something like that, you need to reduce your moment of inertia. So the far from the axis will produce higher moment of inertia. If you reduce the distance towards axis, you will reduce it. But for example, for this, the third picture will shows you will have a higher rotation. Same the concept of the Bailey just now. Okay, this is the graph shows that the relationship between L is I times omega, radian per second, and your moment of inertia. If you notice here, okay, in order, for example, you are flipping from this position to this position, what happen is by changing the what we call it, the formation, you've noticed the blue color shows the omega and red color shows the moment of inertia. So when you have a low omega, you have a higher I. So the peak happen at this position because of your I is the smallest distance from your center. So you produce higher lower I, lower in moment of inertia. This is the lowest point, produce the highest rotation of omega, angular velocity. So this is shows that when we constant the L, means as we know that L or M equal to I d omega dt. So when we remains this as a constant, this is constant, so you can see that the relationship of I and omega something like this. So when you have the lowest I, this is the lowest point of I, produce the highest omega. Okay, so this is the relationship of moment of inertia and also angular velocity towards the net of torque. Okay, so next we will learn about how to choose a control volume. See, a control volume is, what is control volume? I think I have explained it previously in last chapter. Okay, is to create the mathematical model of physical process. So it is an initial frame of reference. It is a volume fixed in space or moving with constant velocity through which the fluid or gas liquid flows. So for example, if you have a pipe here, jet flow pipe, so okay, for example, so you can say that you need to set up which is your control volume. For example, the control volume is this area, because this is the most important of in order for you to calculate your pressure, your velocity and the rest. On top of this one, this is not your control volume. So control volume, I think I've explained it more detail in previous. Then we will go further in this topic. So a control volume can be selected as any arbitrary region in space through which the fluids and its bonding control surface can be fixed, moving and deforming. So you have three types of control volume, which is fixed control volume, okay, moving control volume and deforming control volume. Okay, so this is extremely important that the boundary of the control volume are well defined during an analysis. For example, if you have a fixed control volume, you need to use a fixed control volume. If you have moving control volume, then you assume it to be a fixed control volume, so the calculation will be wrong. Okay, so first of all, you need to decide or to understand in order for you to decide which is the type of control volume. So the flow rates of any quantity into and out of the control volume depend on the flow velocity relative to the control surface. Okay, this is an example of the control volume. So you have A, B and C. So okay, so this one is in terms of pipe flow. This we call it as a fixed control volume. Okay, so then we have an engine. So this is a moving with respect control volume, and this one is deforming control volume, something like balloon. So means that the balloon, the volume of your volume of your air inside is changing based on the deforming of the balloon. So this one is deforming control volume. So for example, this is the fixed control volume. Now as an example, the pipe flow in pipe is a fixed control volume, which is we know that the control volume remain in this region of the pipe, the size of the pipe. So this area we call it as a surface pipe. Then inside is we call it as the fluid, surface of fluid at the end of here, or this is your surface of fluid and this is your end of surface of fluid. Number one is beginning of surface of fluid. The number two is the end of surface of fluid. So this type is we call it as fixed control volume. Means that your control volume remains the same size of the pipe. So it's not keep on changing unless I change this pipe from PVC to a elastic pipe. For example, your elastic pipe, something made from for example made from rubber. Okay, like so your pipe, this is an example, your pipe will be changed based on the pressure inside. So automatically your control volume are not in category of fixed control volume. Okay, something like deforming control volume. So that's why you need to understand your situation. Okay, so this is, for example, when high pressure, so this pipe will be increased the deformation. So we call it as a deforming control volume. But for normal pipe, for PVC pipe, for galvanized type or something about pipe, is fixed control volume. Okay, the second one is fixed or moving control volume. This is the second picture, which shows that, for example, this is your jet engine. So we take it this area as your control volume, which is you have an inlet here. This is your control volume, the dotted line. Okay, control volume of the engine. This is your outflow. So means the flow moving, okay, not inside but is through and outside. So we call it a fixed and moving control volume. Okay, so this one is flow in pipe is fixed control volume. So the control will be inside of the pipe. This one is outside the pipe, is more on moving control volume. The third one is deforming, something like balloon, like I said previously. The volume of the fluid will be changed based on deforming of this balloon. So this we call it as deforming control volume. Same like this concept. If you change a little bit, we use it a flexible pipe, for example, then it's very flexible, something like from rubber, something like balloon, it will change. So this is not already fixed control volume, it become deforming control volume. Okay, this is an example of fixed control volume. Okay, this is the fix of a tripod is used to hold the nozzle. Okay, so now we want to calculate this area, so we need to determine our control volume. So in this case, the control volume will be here until here. So the rest we don't want to, we can ignore. We just focus on here. The most important thing, you have all the informations of inlets. This is for example inlets, then your outlets, then you can calculate the pressure, velocity, and the rest. Okay, so the water velocity relative to the ground is the same as the water velocity relative to the nozzle exit of the plane. Okay, this is moving control volume. For example, you have a moving control volume of an aeroplane. Okay, so the entire control volume move at a velocity of control volume, which is relative velocity becoming V relative is equal to velocity minus velocity control volume, whereas V is the absolute velocity of the exhaust gas and the velocity relative to fixed point on Earth. Okay, VR we call it as relative velocity of the control volume. Okay, for example, in order to calculate this one, the main formula is VR equal to V minus V control volume. So means V relative, okay, this is the main equation. V relative, velocity of relative, is equal to velocity minus velocity of control volume. In this case, for example, we take it the whole aeroplane as a control volume. This is your control volume. So we know that the aeroplane will move to the left. So means that our control volume will be moved to the left. So the velocity of control volume, the direction become towards the left. Okay. In terms of VR, V relative is, for example, the engine. The engine will produce thrust. Okay. Then the relative velocity relative is direction is toward the right. So then automatically the velocity of this aeroplane is of this engine produce a velocity of towards the right, means that the effects of the engine. Okay, for example, if the aeroplane is cruising at 500 km to the left, okay, 500 km moving to the left, and the velocity of exhaust gas is 800 km per hour to the right. Okay, the velocity exhaust gas relative to the nozzle exit is VR equal V minus VC. So we know that our velocity of the exhaust is 800, for example, I. Okay, minus, we use the minus VC. In this case, our VC is 500 km per hour. But we need to understand the VC become negative because of the direction of VC towards the left. So this every direction on the right become positive, any direction towards the left become negative. That's why you should put negative in control volume. At the end you get 1300 km per hour. Okay, so in order for the moving control volume, you need to determine a correct direction of each VR, V and VC. Okay. Okay, next. This is deforming control volume. This is an example of a piston. This is your control volume inside of this piston area, okay, when analyze the exhaust gas from a reciprocating internal combustion engine, a wise choice for the control volume is one that comprises the space between the top of the piston and the cylinder of the head. So this is the area of combustion happen. So that's why your control volume, okay, that's why your control volume is this area. So when the piston move, okay, in this case when the piston move, we know that the control volume keep on changing. So it keep on changing based on the area of the combustion area. So that's why this type of concept we take it the control volume as deforming control volume. Okay. So this deforming control volume is due to the control surface move relative to the parts. Okay. Okay, we go for this example. This is for moving control volume. Okay. We go for example number 1. Okay, you have a car. There is a person in car which is 20 meter per second. Okay. And this person throwing a ball with 10 meter per second towards a person. Question number 1. So in order for that, how to calculate that? We know that VR is equal to V minus V control volume. Okay, in this question number 1, okay, in order for VR, which V relative to A, okay, VR are relative for V, this volume relative to A, okay. So we know that the direction to the right is positive. So VR equal to V, our main velocity is the direction of the car become 20, the direction of the ball plus it become 10, minus V control volume is 0. So the answer should be 30 meter per second. Okay. For VRB, just now VRA, our velocity is towards B. Okay, the velocity of the person and the ball become 20 plus 10 meter per second minus control volume towards B. B is 5 meter per second. So, but the direction of B is towards the left. So, should put negative. So, at the end, you will get the answer of you will get the answer of 35 meter per second. And the third one is VRC. Your V is 20 plus 10 meter per second minus your V control volume is the direction of the people is to the left. So negative 5 meter per second, but the roller moving to the right of 10 meter per second. So right, it should be positive of 10 meter per second. So at the end, the answer you will get 20 minus 5 at the end. Sorry, 30 minus 5, you will get 25 meter per second. Okay. Okay, you get 30 minus 5, you will get 25 meter per second. So understand. So based on this formula, VR equal to VR vector to the right equal to V minus V control volume. So you need to define the condition. For the A case is there is no movement of person, so V control volume, your control volume here will be 0. Okay. In this case, your control volume start to move to the left. So minus, you should put minus of control volume because it's moving to the left. So the total velocity of the ball acting towards this person is 35 meter per second. Okay, but the third one, even though he moved to the left 5 meter per second, but this roller moved to the right of 5 meter per second. At the end, we know that it will be 5 meter per second towards the right. So the velocity of 30 minus 5, so at the end is only 25 meter per second. So means the velocity impact toward this person is lesser than the velocity impact towards the B person. Okay, this is the concept. Okay, understand? Hello? Everybody can hear me?
Yes, doctor.
Okay. So this is the concept of relative. Okay. Okay, this is the video. Maybe you can follow it